Well, we looked at differentiating trig. Let's go back the other way, basically the reverse operation. So as we now know how to differentiate, integrating should be straightforward. We saw that when we differentiate sine, we got cosine. Therefore, logically, we integrate cosine, we get sine. Now, I'm just dealing here where the angle is a linear function, and so we'd have 1 over the coefficient of x out the front there. Now, sine. We saw that when we differentiate cosine, we got negative sine. Therefore, when we integrate sine, we should get negative cosine. And this is where we really have to be careful, because that's so easy to make that mistake. Remember, it's when you differentiate cosine, you get negative sine, but when you integrate sine, you get negative cosine. And then the third one then, sec squared. Well, we saw that when we differentiate tan, we get sec squared, so logically integrate sec squared, you get tan. As I say, that's just for linear functions. Let's do some examples. So integrate sine 3x. As I say, this is where we've got to be careful. Integrate sine will go to negative cosine. So we'll have negative 1/3 the cosine of 3x. Cos of 1 minus 5x, oh well, added thing here is that the coefficient of x is negative. So integrate cosine, it goes to sine, but the coefficient of x is negative, so we will end up with negative 1/5 the sine of 1 minus 5x. And let's do a sec squared. Integrate sec squared, well that just goes to tan, so we get 2 tan x on 2. Let's do a definite one. So integral of sine 2x. Sine goes to negative cosine. So we have minus 1/2 cos 2x. Substitute in our values and we get cos of pi minus cos pi on 3. We're going to see these numbers come up a lot because they're our exact values. So they happen a lot in questions. And cos of pi is -1, cos of pi on 3 is 1/2, and we end up with 3/4. Now, as this is a definite one, it's a good point to note right now, radians. Okay? We use radians, because remember how we derived them in the first place. It all came from the area of the sector, and that formula worked when the angle was in radians. So whenever we're doing calculus and trig, we make sure our angle measure is radians. Alright, let's have a look at one where it's not a linear function. And the idea becomes very similar to what we saw with logs and exponentials, and we simply say, well, what we would like out the front is the derivative of the function. So the angle in this case is x squared. The derivative of x squared would be 2x. So I'd like 2x out the front. Well, I've only got 1x, so I've got 1/2 of 2x x squared x squared. So it's in the form of derivative times sec squared, so that will go to tan. So we have 1/2 tan x squared. Sine squared. Now, get ready for that integral, or cos squared. It will appear somewhere. They love asking it. Certainly in extension 1, because they want to say, well, okay, do you understand how to convert things and things like that? This is where our double angles becomes very useful, because we change the sine squared, and remembering, cos 2 theta could be cos squared minus sine squared, but that therefore means I can rearrange it and say sine squared is 1/2 of 1 minus cos 2 theta. And if it was a cos squared one, I could go 1/2 of 1 plus. So the sine squared goes to 1 minus, the cos squared goes to 1 plus. That means I can change my integral to be 1/2 of 1 minus cos 2x. It's now a nice neat trig to integrate. So I get 1/2 of x minus 1/2 sine 2x. I've expanded out. Do you need to? Probably not. But there it is, x on 2 minus 1/4 sine 2x. What about tan x? This is an integral that's well worth remembering, because it will come up a lot, the integral of tan x. And how do we get it? Well, let me show you how you get it, and then we'll never use this again. Alright, we change tan to sine on cos. I now have a situation where I have derivative on function. Well, almost, because the derivative of cosine is, of course, minus sine. So I can change that to be the negative of the integral of minus sine on cos. Derivative on function, log situation. So it's minus the log, technically the absolute value, of cos x. So minus the log of cos. Of course, the other way you could write that, if you don't like the negative out the front, is the log of sec. So you bring the -1 inside the log, the reciprocal of cosine is sec. I would not be doing that every single time. I would just be remembering integral of tan is the log of sec or minus the log of cos, whichever you prefer. Of course, if they do ask us to derive it, all right, we need to know the technique, and there it is. But it saves a lot more time just knowing it. Okay, here's, hang on, cos x sine to the power of 7x. See, this is another one where let's set it up so it's derivative times some function to a power. So that reverse idea of the chain rule. And cos is the derivative of sine, so we've got the derivative out the front. Now if you don't see it, we do a substitution. And the substitution, well, what's causing the problem? Well, it's this sine being to the power of 7 that's causing me the problem. So I'll make u equals sine x, which means the u is cos x dx. It's a definite one, so if I'm going to do a substitution, I need to substitute in for the limits as well. So when x equals 0, u equals 0. When x is pi on 2, u will equal 1. And I can change this to the integral from 0 to 1 of u to the power of 7. Add 1 to the power over the power, substitute in, we have our answer. So if I wanted to do it by substitution, that's how I do it. If I recognize it straight away, then it's probably quicker because I say, oh, well, I've got derivative times function to the power, so I know that function, I just add 1 to the power over the power. I get an 1/8 of sine x to the power of 8, and then I can substitute in the limits I've got at the start. Okay, 2020 HSC. Cos 5x sine 3x. Product to sums. This becomes 1/2 sine plus sine. Now did it go again? Half, so sine the difference plus sine the sum. Actually doesn't matter because it's plus, so whether you do the difference first or the sum first. Now I take advantage that sine being an odd function, so I've changed the sine minus 2x to minus sine 2x, and now I can integrate each of those. I get minus 8 cos 8x plus 1/2 cos 2x. Substitute in pi on 2 and 0, and we have our answer. Now remember, those formulas, well, half of those formulas are on the reference sheet. I think it's this way round, it's on it, isn't it? It's the products to sums is on the reference sheet, but the sums to products is not on the reference sheet. No. So let's add 7D and 7E.